We're good. All right, we were looking at, and I left my pens in the office, so let's hope again that we've got something that's legible. We were looking at VSEPR when last we met. Yeah, that'll work. Shapes from Lewis structures. It must be exceptionally humid today. I may just let y'all be a little fuzzy because otherwise I can't see you at all. Let's try that one more time. I'll run them way down on my nose, see if that'll work. And we looked at this concept again of a steric number. That's kind of where we halted pretty much. We looked at a couple of cases, but steric number again. The number of things attached to an atom. And again, as we talked about that, that's another atom or a lone pair. And again, to use carbon back as an example, so again, the steric number on carbon here is 4. It's attached to 4 things. Here it's attached to only 3 things. And then in the case of CO2, the carbon is attached to only 2 things. Now again, you're going, how do multiple bonds come into this? They really don't. Okay, the thing is, how many other things are attached to the atom? That's the steric number. And the major premise on VSEPR is that the electron pairs will try and spread out to reduce their repulsion as much as possible. And so we began to look at a steric number. We looked at 2 and at 3. Again, we drew a model. We declared what the geometry was, and I put the word electronic up here because we're going to expand that discussion today, also talking about what we're going to call molecular geometry. Often they're the same, but sometimes they are not. Again, I heard me bouncing off of that back wall, but I'm just trying to make sure I'm loud enough for the folks that are far away to hear me. Okay. I'm still not fully comfortable with this technology. You figured that out, so just bear with me and everybody will be okay. All right. And then we looked at some examples because examples are usually a whole lot better than the rest of that. So if we've got 2 things, then our model should look like this. That's 2 things attached to a common third. And the electronic geometry there is just linear. And again, we looked at a couple of examples. Here is kind of the classic ones, something like carbon dioxide, hydrogen cyanide. We will look at some examples today of things with 3 atoms that aren't linear. Okay. But if we've got 3 points, again, we go back to our high school geometry class, 3 points are either in a straight line or they're not. Okay? So that's what we're going to argue with 3 atoms. The 3 atoms will either be collinear or not. Okay. Now, with a steric number of 3, we have 3 things attached. By the way, that's 180 degrees. I'm not going to ask you to come up with those numbers per se, but it's a nice thing to have just stuck in the back of your mind because it gives you a general idea of what the shape is going to be. And if you're a numbers guy like me, it's really good. Here it's 120 degrees. And again, if you remember, and you probably do, that there's 360 degrees in a circle, divide by 2, you get 180, divide by 3, you get 120. Okay, so it's going to go on down the line. And we call this trigonal or triangular planar. Again, it is just that. It is just the shape of a triangle. If it is perfectly symmetric, if the three things that are attached are all the same thing, then our real-world experience tells us that it is a perfect isosceles triangle. It just fits inside a perfect triangle. If it's something like formaldehyde, where two of the things are the same, there's two hydrogens and then an oxygen, so it's two of something and, then the triangle tends to be extended because the carbon-oxygen bond is different than the carbon-hydrogen bonds. Now, we need to look, we're going to go from here then, so if we have something like this, there's BH3, that's a great example. Or we could have something like this that we just talked about, there's formaldehyde. At this point, I want to extend this discussion just a little bit, and I want to look at sulfur dioxide. There is sulfur dioxide. You can go back and check if you don't believe me, but that is the right Lewis structure for sulfur dioxide. There's 18 electrons up there, and 6 and 6 and 6 are 18. The sulfur is undergoing valence expansion, but that's okay because it's on the third row of the periodic table. Okay? I don't know if, okay, yeah, I still have good sight lines. Okay, should put tape down where those things are so I know to go there. There's sulfur, they're on the third row, so it's good to valence expand. Expand, sorry, West Texan. Expand. I do know how to speak correctly, I promise. Central sulfur came with 6 electrons. It makes 4 bonds and has a lone pair, so it's a counted 6, so no formal charges. This fits all our bills. Okay, everybody has an octet, nobody has a formal charge. Best Lewis structure ever. Okay, but let's notice, still has a steric number of 3. Still has a steric number of 3 because there's 3 things attached, 2 oxygen atoms and a lone pair. Okay? So, I meant to get these built yesterday and I did not, so pardon me for just a second while I pull the toys out and we'll get it built. And if I could just find the bag of connectors, I'd be set. There they are. Okay. We're about to get to the point where we've got to look at things in 3 dimensions. Okay, I'm trying to get... This is the right height for those. It's the wrong height for you on the back row, but look around. It'll be okay. There's no living in a perfect world. There ain't no perfect world anyway. All right, so there we go. Come on. Ya-da-da-da, ya-da-da-da-da. Don't mess with me. Can you tell how hard it is for me to be quiet? That's why I talk to myself, because I just can't stand quiet sometimes. But for just a few seconds there, I just was working and not talking at the same time, and you were going, it is possible. He can. Shut up. All right. Here we have then what I would consider, look, it's planar, it's flat. There's a trigonal planar, electrons, electrons, electrons. In what we've got here, Okay, I hope those, have they fixed that? Oh, they have, good. This is the second generation of these. There then is what I would argue is what sulfur dioxide ought to look like. Works better perhaps if I hold it out to the side. There we go. Okay. There are three things attached: oxygen, oxygen, and a lone pair of electrons. The electronic geometry, where are the electrons? Trigonal planar. What's the shape of the molecule? The fancy word is nonlinear. The four-letter word starting with B and ending with ENT is bent. Okay? If it's three atoms, it's got two choices, linear or not. So we'll call it linear, and this, I just call this bent because it makes my life easy. It's a whole lot easier to say than nonlinear. So bent. So trigonal planar electronic geometry. No lone pairs, then the geometry is trigonal planar. That's these suckers. One lone pair, the molecular geometry is bent. My suggestion to you is always just learn the base geometries. And then just start covering up and seeing what's left, and you'll see what the molecular geometry looks like. Okay. If you go, okay, great, there's three groups, it's trigonal planar. What if one of them is a lone pair? What's left? Bent. Okay. If we had two lone pairs, it'd be a moot point because it'd just be two atoms and 2 points constitute a line, so we'd never go there. Okay, but that's what you've got. When we get to a steric number of 4, well, I guess I should pause and ask for questions. I actually really should pause and let you finish writing. I'll build toys. You write. Yes, ma'am. Mia.
So does the bent fall under the trigonal planar? It's just
Yes, ma'am. So in the case of a steric number of 3, there's two possibilities. There are 3 atoms, no lone pair, and then the molecular shape is the electronic shape trigonal planar.
Okay.
If there's one lone pair, then one leg of that triangle is now a lone pair, and what's left, the atoms, then form a bent line.
But the electric geometry is still trigonal.
The electronic geometry for 3 is trigonal planar, period. Okay. Yes, ma'am. You have parsed your way right through it. Good job. All right.
Are there multiple molecular geometries for steric number 2?
No, ma'am. Because, again, they're either both atoms or one's an atom and one's a lone pair, and they'd still be linear. And if one's an atom and one's a lone pair, then you still just have 2 things, and it's a straight line. But yes, ma'am. Now, if we go to a steric number of 4, we find that we leave, if we have a steric number of 4, we have to leave 2-dimensional space, 3-dimensional space. The simplest thing for me to do here is to show you what the shape is, and then I'll show you how we draw it and how we talk about it. If I attach 4 things to a common fifth, so I'm going to have one atom that's attached. Okay, I'm trying not to break this or bend it, and it's just not going on at all. There we go, see? That would probably have been the easy thing to do, is to put these on first. I apologize for not getting to this. I intended to be down here 5 minutes earlier, but my student who is taking my PChem class from Nebraska, this was our only chance to holler at each other before Tuesday, was this morning. Okay, there we go. if we're going to attach 4 things to a common 5th thing and let them get as far away from each other as possible, this, and I promise you, this is a very common geometry and it's quite stable. It's just not in this toy, okay, in this molecular model. This is the shape that we will get. And again, for those of you videoing in this morning, I'm going to kind of turn it back and forth a little bit so you can see it. It is a triangular, it's like a tripod. Much like the iPads are sitting on, you're watching me on, this is like a tripod. So I've got the 3 feet and then the pole up top, okay? If I draw this, I'm going to set that down there. You can't see it. There's the only upside. Nope, you're just not going to see it. Be all right. If I draw this, I'm going to do this sort of representation. Here are, and I'm going to use a wedge and a dashed line. And at the risk of sounding silly, this is how we describe this. This is called wedge dash representation. Yeah, we're really tricky how we name things, we chemists. Okay? So what's going on here? You've got one straight up. You've got one straight to the left. Then there's this one that projects, sticks out. And then there's this one, like my hairline, that recedes. Okay? That was, for the guys in the audience, that was the joke. The women are going, receding here? Oh, okay, yeah. It's okay. And again, the idea is to force that perspective. Wedges are in front of the board, dashes are behind the board. So we're just trying to represent a 3-dimensional structure in 2-dimensional phase space. Okay, so this is that. So I'm going to try and stand, there we go. Pivot back, thank you. All right. So this is that. The fact that those are white, they don't show up in a lot of contrast on that whiteboard. So in the video, we'll hope that it looks all right. This is called tetrahedral. Big fancy word, okay? This has an electronic geometry that we call tetrahedral. And we'll see how my artistic abilities are today. And they're pretty poor, because I can't even draw one. Okay, let me duck. That's going to really mess with the robot back there, no doubt. There we go. This is a tetrahedron. Tetra, prefix for 4, as in the game Tetris. And if you've never stopped to think, go back and play Tetris again real quick and realize, oh, all of the pieces are 4 squares. And if you've never noticed that before, now I've completely ruined the game of Tetris for you, because you won't be playing Tetris. You'll be going, look, 4, 4, 4. That's why it's called Tetris. This is a tetrahedron. And notice then that this tetrahedral structure fits just inside that tetrahedron. And so to describe it adjectively, it's tetrahedral. The bond angles here are 109.5 degrees. Again, I don't care to have you memorize numbers just out of hand, but that is a tetrahedral bond angle of 109.5. It's perfect. It gives us a totally symmetric molecule. If I spin it by 1/3, I get it back. If I spin it by 1/3 through that one, I get it back. If I spin it by 1/3 that way, I get it back. It's completely symmetric, meaning that each one of these atoms experiences the exact same electronic field. And that makes it the most stable structure possible. And again, that's called tetrahedral. I am going to take this information, I'm going to move it, because we're out of space. I want to leave that up there. I'm going to come back over here. Again, just having gone through some of the recordings from earlier, if I get too wide, it's just not a good recording. So here we go. Just going to continue this table over here. Steric number, model, electronic geometry, molecular geometry, and examples. Steric number 4, again, my model looks like this. That's 109.5 degrees, and we call that tetrahedral. My electronic geometry for 4, when I say tetrahedral, I mean steric number of 4. When I say steric number of 4, I'm saying tetrahedral. Electronic geometry for steric number 4 is tetrahedral. And if it's tetrahedral, we know it's got a steric number of 4. Tetras, 4. That's why I beat that one to death, so hopefully you can file that one away. So if there are no lone pairs, okay, so that looks something like this. Here would be methane that we looked at earlier. This is technically a proper model for methane because we use the black to represent carbon and the white to represent hydrogen. We're eventually going to go back and tie quantum mechanics back into this just a little bit and come up with another label for this. But if I say tetrahedral carbon now, you'll know, okay, it's bonded to 4 things. Okay? A trigonal carbon would be bonded to 3 things. And a linear carbon would be bonded to 2. That's what carbon can do. Can be bonded to 4 different things, it's tetrahedral. Bonded to 3 things, it's trigonal planar. Can be bonded to 2 things, it's linear. That's it for carbon. And again, I'm just trying to front load carbon for you because most of you have got organic. Okay? And you will eventually thank me. Got a note back from a MD student after his second year of med school. He sent a message back from one of my colleagues, and he said, so-and-so said to tell you that he used to hate you, but now you're not so bad. Okay? I took that as a compliment. He'd gone through medicinal chemistry and realized he really needed all of that junk I'd made him learn. So, now, what if I have one lone pair? So what I'm going to do now is regretfully then take this back apart a little bit. Here again, and I chose a poor shirt to use this model. There we go. Yep. Oh, just live with it. Okay. I've just pulled off one of the atoms, so now I have 3 bonded atoms and a lone pair. Okay. The shape of the molecule now is just a triangular or a trigonal pyramid. It's just a pyramid. It's squashed, but it's just this pyramidal shape. Okay? So if we have one lone pair, we describe that shape as trigonal pyramidal. And if that language doesn't stick on your tongue, well, it just does. And our go-to example there is, again, a simple compound with which we're familiar, and that's ammonia. And again, to kind of speak to Mia's question from earlier, hey, the electronic is still tetrahedral, but one of those positions, in this case, I've drawn it at the top one, it's a lone pair. So if we look at just the molecule, and the molecular geometry is just that, we're just looking at the atoms, then we would consider that to be trigonal pyramidal. It's also possible for there to be 2 lone pair. So again, let's look. Still have the tetrahedral geometry, still got 4 things attached, but now 2 of them are lone pair and 2 of them are not. So if I just look at what is left, I'm going to drop it, but I don't want to. There we go. The shape of the molecule, bent again. Okay. With 2 lone pairs, so there's tetrahedral, okay, but 2 of those are lone pair. So if I look at just the atoms, what's left? There's 3 atoms now, and it's bent. So with 2 lone pair, the molecular geometry is bent. And again, our classic example there is our good friend water. Our go-to there with, here we go, our go-to there with a steric number of 4, but 2 of those are lone pair, that's water, and that's bent. So, if I don't have lone pairs, let's recap. Then we're going to look at 5 and 6 quickly, but quickly being a relative term. If I have 3 atoms, if they are the only thing attached to the central atom, then they're going to put themselves at 180 degrees. Okay? If there is something else on the atom, okay, if there's something else on the central atom, a lone pair of electrons, that's going to push those atoms away, and now it's bent. Okay? So linear, bent. Now, steric number of 2, it's 180 degrees. If I put a lone pair on there, then that's going to go down to about 120 degrees. And again, I'm going to say something here that is not, again, I don't concern yourself with the numbers, but just know this. Lone pairs like more space than bonding pairs do. Lone pairs will push it down. So instead of being 120 degrees, in SO2 it's about 115. Okay. In water, I've got a lone pair here and a lone pair here, and these get pushed even further down. And the bond angle in water, this bond angle is 104.5, as opposed to the pure tetrahedral of 109.5. I don't care if you remember those numbers or not. I care that you go, oh, lone pairs take up more space. So that's going to close things down. Grace?
Does that mean that the lone pairs are closer to the central atom if they take up more space because they're not being shared? Because they're not having to go back and forth?
I'm hearing your question, and I'm thinking, so you can't hear the wheels turning, but they're turning up there. Are they closer to the central atom? Okay. I believe so. I am not sure. I'm fairly sure that no one has ever asked that question in my 35 years of teaching before. I can't remember it anyway. I'm not sure I have ever asked that. So one, congratulations on a really excellent question. Okay, let's consider the fact that if they belong to the oxygen themselves, then oxygen ought to be exerting a larger force on them than they would on the shared electrons. I'm going to go with, I'm pretty sure the answer to your question is yes. Is that cool? If I find out differently, I'll tell you. If I don't, then we'll go with that.
Okay.
All righty. Other questions? Okay. So if there's only 2 things attached, it's linear. If there's 3 things attached, it's trigonal planar. Okay, there's the third thing. Okay. The thing's up here. And otherwise, it's tetrahedral. Okay, you can't see. I got 1 foot front, 1 foot back, and arms over here. Okay, so then it's tetrahedral geometry. If my hand is the fourth thing, okay, I mean if my arm rather is the fourth thing, or I could simply pick this back up. Look, tetrahedral. If they're all atoms, then the molecule itself is tetrahedral. If one is a lone pair, triangular planar. If two are lone pair, bent. Okay, hold that out to the side. There we go. It's all right? Okay. In organic chemistry, where everything is based on carbon, this is really what you need to know. As we look at more complex species where we have valence expansion, then we're going to find that we can also see steric numbers of 5 and 6. I'm going to make the models, we'll sketch them on the board, we'll look at one example or two of each one, and then we'll go, okay, there might be one question on that on the exam, but it's probably going to focus on 2, 3, and 4. Okay, and that's just the truth, so that's what's going to happen. So let me grab, a couple more of these, and let's look at a steric number of 5. We saw one of those the other day when we were looking at PCl5, phosphorus pentachloride. Okay, and so now let me build that particular species. Okay, yes, a whole back, there we go. Had to pull out 27 to get 2 of these. Here is what a steric number of 5 looks like as soon as I can force these atoms on the end. Getting better. Chemical Lego, okay? And a steric number of 5, okay, looks like this. You'll notice that there's one straight up and one straight down. So it's linear, like a steric number of 2. And the other 3 are trigonal planar to each other, like a steric number of 3. So at the risk of being duh, what is 5? 2 plus 3. If we know that 5 is 2 plus 3, then we know that the model is the model for 2, linear, crossed with the model for 3, trigonal planar. Now, notice if I cover up the bottom, that's a triangular pyramid. That on the bottom is another triangular pyramid. And so we give this the very simple name of trigonal bipyramidal. Sometimes I have to apologize for what we do in chemistry, and this is one of those cases. So I'm going to erase 2, 3 in this first version of 4 over here so we can put 5 up, 5 and 6. You can back up the video if you're watching it there, or you can look back down at your notes where you have, I know, carefully written it down. With a steric number of 5. Okay. The model looks like this. And we call this trigonal bipyramidal. Bless you. Let me also point out that there are some really good online resources, particularly at Khan Academy. I can't remember whether it's com or org. It doesn't matter. Just put KAHN, Khan Academy, and type in VSEPR animation. Okay, and it will bring up some nice, some three-dimensional stuff, and you can see, and they'll rotate it for you. There are some websites, if you just throw that into Google, where you can use your mouse to move the molecule around. during the exams, if you're taking the exams present and you want to come up and play with the models or take them back to your workspace, that is just fine. I will have these. I've also got a much smaller set. This size, I've got a set of these as well, and you're welcome to play with those as well. And I'll take them home and put them in the dishwasher, when everyone's done playing with them. We'll just, after class, first thing you do is just go wash your hands, right? We'll be paranoid and life will be good. Coronavirus does not live long on hard surfaces, so we're good. All right, so that's trigonal bipyramidal. And if there are no lone pair, then the molecular geometry is also trigonal bipyramidal. And again, our go-to example is going to be a pentavalent, that is to say, bonded to 5 things, fluorine. PF5. Okay. That would be trigonal bipyramidal. If I have one lone pair, I'm just putting the lone pair of electrons out there in a balloon, okay? If I pull my model back up and say, okay, what if one of those is a lone pair? And then the question is, what if he could actually pull that off so we could see it? Great. So what if one of these is a lone pair? Okay. So I've just replaced, and notice I took one of these because they're further away from their neighbors, and this lets the lone pair have more space. Okay. Notice this. What is that?
Seesaw.
It's a seesaw. What do we call this geometry?
Seesaw.
Seesaw. This is seesaw or teeter-totter geometry. Okay, that's what we call it. Why? Because the English language still is prevalent worldwide and we got to name it. And it's the simplest thing. I mean, how else are you going to describe that? Lever and fulcrum geometry. Let's go with seesaw. So the geometry here is just that. It's called seesaw. And my go-to example there is going to be something like this. I'm not going to put the lone pairs on the... Oh, I am too. I lied. Because otherwise somebody will go, aren't there lone pairs on those fluorines? Yes. This is sulfur tetrafluoride, SF4. Where will we see steric number of 5 most commonly? Phosphorus bonded to 5 things, sulfur bonded to 4 things with a lone pair. Okay, 4 atoms, 1 lone pair. It is possible for there to be 2 lone pair or even 3 lone pair. Okay. If there are 2 lone pair, again, I'm just extending this picture. If there are 2 lone pair, there is our so I've got a lone pair of electrons in the front. I've got a lone pair of electrons in the back. And what's left so here again, steric number of 5. 2 of those are lone pair. What's the molecule shaped like now?
Triangle.
What's it look like? Let me draw this shape. Here's what's left molecularly. This is my This is where my molecules are. T-shaped. I know it's too simple. You're going, I wanted it to be harder than that. I'm sorry. It's just shaped like the letter T. T is for Texas. T is for Tennessee. You may not know that song, but I do. Okay? I'm from Big D, my, oh yes. All right. So it is just T-shaped. And it is here, I'm going to stop drawing on the board after I draw this one, because these compounds really exist just so we can talk about them in VSEPR terms. Here is the oh so common molecule that you have seen so many times, iodine trichloride. You're going, that exists, that's a thing, that is a thing, it does exist. Okay, but that's it. And you're going, you've gone a long way to come up with that example. Yes, yes, I have. If there is a third lone pair, I'm not drawing this on the board. If there's a third lone pair, what's left? Linear. Okay. Because if the third lone pair, they're left two things, that just means two atoms attached to a common third. And the way to do that and give the lone pair, we put the lone pair in the triangular positions, and what's left is linear. Okay? Because we have all taken math classes, I'm not going to build the 6. I'm going to draw you the 6 and talk about it real quickly. There's really just one case that's critical, and I'll show you the 2 subcases. So that's number 5. I'm now going to erase steric number 4 over here so that I can show you 6, and we will be done. Steric number of 6. There is a steric number of 6. Think 3-dimensional Cartesian coordinate system. Okay? One up, one down, one front, one back, one left, one right. So it's just like there's one at the top and the bottom of the z-axis, one on the left and the right of the x-axis, and one in the front and the back of the y-axis. The fancy name for this geometry is octahedral. There is an octahedron, an 8-sided figure. Your hands actually do a pretty good job at that, okay? It's 2 4-sided pyramids, 2 Egyptian pyramids, base to base. That's an octahedron. If we've got any Dungeons and Dragons devotees, then an 8-sided die, you know what an octahedron is. Okay. It's interesting to me, when I was 6, Dungeons and Dragons were huge. When I got to be 16, Dungeons and Dragons were huge. I got to grad school and they tried to drag me in when I was about 25 to a Dungeons and Dragons group. Then 20 years later, when my son hit college age, Dungeons and Dragons are back. So like every few years, it just comes back. I bought my son a full set of die for Christmas one time. He was thrilled. 8-sided die. It's an octahedron. If there are no lone pair, then my molecular geometry is octahedral. And our classic example there is, and I am not drawing the lone pair on the fluorines, is sulfur hexafluoride, SF6. Everything is at 90 degrees to everything else. You knew that because it's a Cartesian coordinate system. By the way, I learned this after I started teaching. Why is it the Cartesian system? Because the French mathematician René Descartes was the one that thought it up. So it's Cartesian because it's after Descartes.
Is that supposed to be tracking on you at the moment?
Whoops. Hello. Sorry. I don't know what happened. Did we get lost? Appreciate that. I'm wondering, it can't have died. I charged it this yesterday. Okay. Let's see. Sorry, ladies. How long was I out? Not long?
Just like 15 seconds.
Oh, okay. Your good friend Hanson Schmidt came to your rescue and said, is that supposed to be tracking you? Well, yeah. Hey, technology is wonderful when it works. Okay, so that's octahedral. We have to go to some really ugly stuff to get to these other examples, but if you should find yourself, and I get threatened eventually, in an advanced inorganic chemistry class where we talk about some really cool stuff that goes on, but it's well beyond what anyone but a chemist needs to do. If I have one lone pair, then the model just looks like this. And the lone pair's at the bottom, and that's a square pyramid. And if I have two lone pair, that's one lone pair. If I have two lone pair, then the lone pairs go top and bottom. So this is a square pyramid, and so square pyramidal, and this is square planar. I'm not going to worry about examples for those. These last 2 points, these are purely for your edification, not for your examination. It's good for you to have seen it once, but you're not going to be tested over it. I need you to know this basic. So we have steric numbers of 2, 3, and 4 that we see a lot of. We see a little bit of 5, a little bit of 6. Other than that, probably not. There is still some ongoing discussion in high-level inorganic stuff as to whether we really have steric numbers beyond 6, but I don't believe so. Okay? But again, I can always be wrong. It's happened a lot recently. So, steric number 2, 3, and 4, know that inside and out. Here's where we're going on Tuesday next. We're going to look at the shapes, and then we're going to say, okay, great, given the Lewis structure, determine its steric number, determine its shape, and then considering bond polarities, is that molecule polar or not? We can talk about whether a bond is polar just by looking at electronegativities. And then the last thing we'll do is we'll tie this back with quantum mechanics. I'm going to try and do that in 15 minutes using my dog and barbecue as an example. We don't barbecue the dog, but we'll use my dog and barbecue as examples there and hopefully just give you a label. Dr. Boston will give you more of that in organic. I just wanted to introduce it to you. All right? Have a good weekend. Be safe. Stay well. And Lord willing, we'll see you Tuesday.